Good day, everyone. Today, I will be discussing the free vibration of single degree of freedom systems with viscous damping. As part of the course Me22088, my name is Dr. C. Sendamarikannan. I am Associate Professor in the Department of Mechanical Engineering at SVC. We have analyzed undamped systems where energy is conserved. Now, let's move to more realistic scenario, damped systems, where energy is dissipated typically through friction or viscosity. We will focus on viscous damping, where the damping force is proportional to the velocity of the mass. Here, we see the equation for the damping force. It is equal to C times x dot. X dot, as we know, is the velocity of the mass and C is the damping coefficient. The negative sign indicates that the damping force always opposes the motion. Damping coefficient C determines the strength of the damping force. Larger C means a stronger damping force leading to faster decay of oscillations. Now, let's derive the equation of motion for the damped systems. We again apply Newton's second law, but this time we include the damping force in our force balance, summing the forces acting on the masses when it is in equilibrium. The mass time acceleration mx double dot, which is acting on the body, equals the sum of the forces which is opposing the acceleration, that is spring force kx, damping force cx dot. When we write it in the form of equation, we will get mx double dot on one side, that is equal and opposite to cx dot, that is damping force minus spring force minus kx. When we rearrange everything on one hand, it will become mx double dot plus cx dot plus kx equal to 0. Diagram shows the physical system that the mass attached to a spring and a dashpot. Dashpot is a symbol of viscous damper, which provides a force proportional to velocity. This diagram shows the free body diagram of the mass where the forces are labeled appropriately. This equation is the key understanding to the damped vibrations. It is a second order. Second order means x double dot d square x by dt square, and its solution will show us how the amplitude of oscillations decay over time due to the energy dissipated by damping. We have derived the equation of motion for a damped system. Now let's tackle the crucial step, solving it to find how the displacement x changes over time. Our approach starts by assuming a solution for the previous equation, that is, the solution is x of t equal to c to the power c e to the power of st, where c and s are undetermined constants. The idea behind this assumption is that exponential functions behave as a property that the derivatives are just a constant times themselves. This aligns well with the structure of our differential equation, which involves x, velocity, and x double dot, that is acceleration. Substituting our assumed solution into the previous equation, and after some simplification, we arrive at the characteristics equation, that is ms square plus cs plus k equal to 0. This is a quadratic equation in terms of spring constant s. The characteristic equation is crucial because its roots will determine the form of our solution. Solving this quadratic equation for s, we find two roots s1, s2. The roots are given by the formula as shown in figure. Notice that the roots can be real or imaginary or complex depending on the value of the discriminant c square minus 4mk. Each of the roots corresponds to a solution of the form we initially assumed. So we have two solutions, x1 of t, c1 e to the power of s1t, and x2 t C2 e to the power of S2t. The general solution is a linear combination of these two solutions. In the previous slide, we derived the roots of the characteristic equation for a damped system. Now let's put those roots together to form the complete general solution. As we discussed, general solution is a linear combination of the individual solutions associated with each root. That equation 26.4 shows the full general solution. It might look a bit intimidating, but let's break it down. We have two terms, each involving an exponential function. The first term as the root s1 in the exponent and the second term as the root s2. Remember that s1, s2 are given by the expression. So we substitute this in terms of s1, this in terms of s2 in the exponential terms. This gives us the complete form of the general solution. The constants C1, C2 are arbitrary at these points. They are determined by the initial conditions of the system. Typically, these initial conditions are the displacement and velocity of the mass at time equal to 0. Think of it this way. The general solution describes all the possible motions of the damped system. But to find the specific motion for a particular solution, we need to know how the system started, its initial displacement and its initial velocity. These two initial conditions allows us to pinpoint the exact values of C1 and C2. Once we have C1 and C2, we have the particular solution for the motion, which allows us to calculate displacement x of t at any time t.
We are about to explore the different types of damping behavior, but first we need to introduce two important concepts: critical damping constants and damping ratio. Remember the previous equation from our the solutions S1 of 2. The term inside the square root is called the discriminant. The critical damping constant Cc is the specific value of the damping coefficient C that makes this discriminant exactly 0. As equation 2.65 shows, setting the discriminant to 0 allow us to solve for Cc. We find that Cc equals to 2 times square root of the product k by m, which can also be written as 2m omega n, where omega n is the undamped natural frequency. Think of it this way: critical damping is the sweet spot. It's the minimum amount of damping needed to prevent the system from oscillating. Any less damping, the system will oscillate. Any more damping, system will return to equilibrium more slowly. Now let's define the damping ratio zeta. Zeta is simply the ratio of the actual damping coefficient C to the critical damping constant Cc. The damping ratio is a dimensionless quantity that tells us how much damping is present in the system relative to the critical damping value. It's a very useful way to characterize damping because it allows us to compare systems with different physical parameters. In this slide, we are going to see the first kind of damping system, that is underdamped system. From the previous slides, we come to know that critical damping constant and damping ratio. In that case, the damping ratio, if it is less than 1, otherwise C, the actual damping provided in the system is less than critical damping value, then it means it is a damped harmonic motion. That means after a period of time, the vibration will settle, its amplitude decreases exponentially with time as shown in this figure. Hence, the frequency will be called as damped frequency vibration, which will be in the form of root of 1 minus theta square into omega n. This graph represents typically the underdamped systems. This is the most practical application oriented system which is used in most of our automobiles. Let's see campus dilemma, a damping solutions for every adventure problem. Dream of every camper, whether they are scaling mountains or enjoying a lakeside retreat, is to connect with nature in comfort and peace. But the reality is the outdoors can be a challenging environment. Forces like bumps, wind, and even gravity can disrupt our carefully laid plans. Core challenge we face is this: how do we create a comfortable and enjoying camping experience? Despite the forces of nature, the answer often overlooked is damping. It's the key to controlling motion and minimizing unwanted vibrations, turning a potentially jarring experience into one of relaxation and enjoyment. Let's start with the basics. What exactly is damping? Think of a shock absorber. This diagram shows how it works. It's designed to dissipate energy, preventive excessive bouncing and vibrations. This principle applies to so much more than just your car. For off-road enthusiasts like those exploring remote trails on ATVs, damping is absolutely essential. Imagine tackling a rocky trail without a proper suspension. Each bump would throw you around, making the ride exhausting and potentially dangerous. High quality shock absorber like the one on this ATV is the solution. It's soak up the impact, providing a smooth and controlled ride, allowing you to focus on the scenery, not the struggle. But damping isn't just for extreme adventures. Even in more comfortable camping setups, it plays a vital role. Consider the struts on your RV's storage compartments or hatch of your SUVs. These gas struts, often overlooked, are a practical damping solution. They ensure easy access to your gear while preventing uncontrolled slamming and potential damage. They are small detail, but they contribute significantly to the overall convenience of your camp. And for a touch of civilized camping, consider something as simple as a door closer. It's another form of damping in action. It ensures a quiet and gentle closure of a tent flap or cabin door or RV screen door, preserving the peace and tranquility of your outdoor retreat. It prevents those annoying slams in the wind that can shatter the serenity you came seeking. So whether you are a rugged adventurer or a weekend camper, remember the importance of damping. High performance shocks to simple door closers. These solutions help us tame the forces of nature, allowing us to truly enjoy the outdoors comfortably and peacefully, because ultimately the best camping experience is one where you can relax and connect with nature, not fight against it. In this slide, I given the examples in the form of your camping adventure. Let's start by examining the basic parameters of the system. We have a spring with a spring constant denoted as K, mass M, and a dashpot with a damping coefficient C. These parameters influence how the system responds to external forces. In our first scenario, depicted, we have a spring mass dashpot system with parameters K equal to 10 Newton per meter, mass equal to 1 kg, C is 0. Then at this time, notice the displacement and velocity graphs. Since there is no damping, it is 0. The mass oscillates back and forth indefinitely, maintaining its energy over a period of time. Now let's shift to the second scenario on the right. Here we have the same spring and mass, but the damping coefficient value of 0.5 Newton second per meter. Observe the change in the graph for displacement and velocity. The introduction of damping causes the oscillation to decrease gradually over a time. This energy loss through damping is critical in real-world applications such as in car shock absorbers, where we need to control and minimize vibrations. Finally, the diagrams at the top of each set visually illustrate oscillatory motion of the mass in both the systems. Comparison between the two help us understand crucial role of the damping coefficient in modifying the system's behavior. Understanding these principles enables engineers to design systems that can withstand and mitigate the effects of vibrations, ensuring the safety and efficiency of various mechanical structures. In this slide, we will explore the difference between critically damped and underdamped systems within the spring mass dashpot framework. First, let me look at the right side. This is the one already we discussed, that is underdamped system. Let me look at the left side of the slide, where we have a system with a spring constant K equal to 10 Newton per meter, mass is 1 kg and damping coefficient is 6.324. See how much the value is very great value. The displacement graph shows in green, the velocity graph shows in red illustrate critically damped system. In this scenario, damping is just enough to prevent oscillations, allowing the mass to return to equilibrium, that is at rest, as quickly as possible without oscillating. This type of damping is ideal for systems where rapid stabilization is desired, such as in some precision instruments or control system like pistols. So, by this slide, we can come to a conclusion that we are having three different types of damping system: underdamped system, overdamped system, and critically damped systems. In the previous slide, we explored the difference between underdamped and critically damped systems. Now, let me explore mathematically. Now, let's complete our picture of damped systems by examining the remaining two cases in mathematical form, that is critically damped and overdamped. Critically damped system occurs when the damping ratio zeta is equal to 1. This means damping coefficient C is equal to critical damping constant Cc. As we discussed earlier, this is the minimum amount of damping required to prevent any oscillations. In this case, the roots of the characteristic equations are real and equal. This leads to a specific form of the solution which won't delve into here, but the key takeaway is that system returns to equilibrium as quickly as possible without overshooting. Imagine carefully lowering a heavy object on a spring. Critical damping is like lowering it in the most efficient way, smoothly, without any bounce, and in the shortest amount of time. In the previous slide, we mathematically come to a conclusion that critically damped system means zeta is equal to 1, C equal to Cc. But in the case of overdamped systems, this occurs when damping ratio is greater than 1, damping coefficient C is greater than critical damping constant Cc. In the case, roots of the characteristic equation are real and distinct because there is so much damping, system return to equilibrium without any oscillating, but it takes longer to do so compared to critical damping. Think of trying to close a door with a very strong hydraulic damper. It will take a long time to close and it won't swing back and forth at all. That is overdamping. So we now covered all the three cases of damping using application scenario as well as mathematically. They are underdamped oscillations, critically damped fastest return to equilibrium oscillations, overdamped slow return to equilibrium oscillations. That is, the key parameter is zeta, damping ratio, that determines which type of behavior we are observing. When dealing with underdamped systems, we often want to quantify how quickly the oscillations decay. The logarithmic decrement is useful for measuring the damping. Logarithmic decrement, denoted by the Greek letter delta, is defined as the natural logarithm of the ratio of two successive peak amplitudes x1 and x2 in a free vibration. This equation shows how we can calculate logarithmic decrement in different forms. Let's break down x1 and x2 represent the amplitude of two consecutive peaks. This equals to zeta omega n and shear d, where this is called as the damping period. Further expanding, we will come to this kind of expressions which may also be used to evaluate logarithmic decrement. This approximations simplifies calculations considerably when dealing with lightly damped systems. All these equations provides different ways to calculate damping ratio zeta if we know the logarithmic decrement delta. If the damping is small, we can further approximate into this much detailed equation. Generalized the logarithmic decrement solutions. Instead of using two consecutive peaks, we can use any two peaks that are m cycles apart. The formula then becomes as shown in equation 2.92, where m is the integer. Logarithmic decrement is a powerful tool for analyzing underdamped systems. It allows us to easily estimate the damping ratio from experimental measurements of peak amplitudes, which can be very useful in practical applications. We came to the end of different types of damping and corresponding equations. Thank you.